The sliding filament theory. We use our muscles for day-to-day tasks, whether it be washing the dishes, walking your dog, or to move around heavy objects.
What?
But have you ever wondered how our muscles contract in order for us to do these tasks? The sliding filament theory is a model that explains just how our muscles contract on a cellular level. Today, I'll be going in depth on how the theory works. Let's start with something familiar. Our muscles. Inside of our muscles, there are fascicles that contain our muscle fibers, and inside of those muscle fibers is where our myofibrils are. Going even smaller, inside of the myofibrils, there is the sarcomere. And inside of the sarcomere is where the sliding filament theory works. There are two proteins located inside of the sarcomere, a thicker filament known as the myosin, and a thinner filament known as the actin. To begin the contraction process, those myosin heads over there must connect to the binding sites on the actin. However, the troponin and tropomyosin located around the actin serve as sort of a wall or barrier, hiding the binding sites that the myosin heads must connect to in order to contract. These exist in order to control the contraction and relaxation of the muscles. In order to begin muscle contraction, the neurotransmitter named acetylcholine signals calcium from the sarcoplasmic reticulum to be released. Calcium acts like a key in order to unlock the walls blocking the way of the myosin heads. The calcium binds to the troponin, which changes the structure of the tropomyosin, causing it to expose the binding sites in order for the myosin heads to bind to. Now that the binding sites are exposed, the myosin heads can form a cross bridge between the actin and the myosin filaments. In order to connect the filaments, the myosin heads use hydrolyzed ATP, which is basically a process where the myosin heads use the stored energy in ATP to create mechanical energy, otherwise known as movement, in order to form the cross bridge. Now that the myosin heads are connected to the actin binding sites, in order for our muscles to contract, the power stroke must happen. In order for the power stroke to initiate, the myosin heads must release the phosphorus and ADP that was connected to them prior to forming the cross bridge. When the power stroke happens, the actin filament slides past the myosin filament, which shortens the sarcomere, making our muscles contract. Phosphorus and ADP are discarded during the power stroke. Now that the actin is sliding past the myosin, it can go two ways. If there is ATP available, then it will bind to the myosin head, causing it to break the cross-bridge link formed between the myosin heads and actin. This essentially relaxes our muscles back to normal, making the sarcomere shrink. When the myosin heads unbind to the actin, then the ATP bound to the myosin heads will again hydrolyze and form phosphorus and ADP, the molecules that were bound to the myosin heads before the power stroke. And now the cycle repeats every time we contract and relax our muscles. That's the way we want to keep it, but unfortunately there is another way that only happens once in our lives. If there is no ATP available to bind to the myosin heads for it to relax, then the muscles will stay contracted, becoming stiff. This is known as rigor mortis, and happens when you kick the bucket. Life crisis out of the way, the sliding filament theory is crucial for the way our muscles operate in our day-to-day activities. Without it, life would sure be kind of boring.